recording? That's what I need, isn't it? Okay, well, I think in the interest of time, we'll get started again. And welcome back, everyone. Hope you had a nice little tea break. Our first session back is going to be about trunk mains leakage. What are the problems at the moment? We're going to be inviting two speakers to the stage now jointly. Carmen Snowden, who's a chartered environmentalist and leads the strategy area of WRC's asset management team. And Anthony Bond, who's worked for WRC for around 30 years and developed the original Sahara pipeline inspection system for detecting leaks in trunk mains. If you'd like to come now, please. Thank you very much. You're going first, I beg your pardon. As long as you don't hold it at the bottom, that's what causes the feedback. I'll give you this just to clip onto your seat.
Oh, right. Okay, hello everyone. So yeah, a bit of a double act this morning from myself and Ant, and we're answering the question, what's the problem with trunk mains leakage, and is it a real problem, which was posed to us. So I'm going to look at this from a flow monitoring perspective, and can we work out the size of the problem if we use flow monitoring and maths, and then Ant's going to talk about some of the practical survey methods to try and quantify the problem in our big pipes. And I think it's for as long as I've been working in the industry, and I think it still is the case, there are some people who will say trunk mains are not a problem, they don't leak. And I think hopefully by the end of my presentation and Ant's presentation, you might have decided that at least some pipes will definitely leak. Okay. So the upstream network, by this I mean trunk mains, but also often service reservoirs, is quite different to the pipes that we spend a lot of time talking about in distribution. So they are, they're big diameter often have long lengths without any connections. The big pipes also have big meters on them, distribution input meters, and then the sort of outlet from these big pipes, DMA meters. They have some directly connected customers. They might be large logged customers, but you might also have a few households just connected to a trunk main because that was the only pipe around, or it could be a legacy issue. They effectively have continuous flow coming through them. So unlike your DMAs where you'd hope that flows drop down, it would still be continuous, but they drop right down during the night. Actually, trunk mains often have flow all the time because they might be doing things like filling service reservoirs, etc. So the flow isn't so connected to our kind of daily patterns of use. And I've already said, yeah, large diameter pipes with different materials, different conditions. I'd say asset records on some of these big pipes are no better than the asset records on many of the other pipes we have. So we have to think about them a little bit differently to DMAs when we want to work out what's going on. And one of the reasons why people are slightly sceptical about the approach that I quite love, which is doing balances across them, is because of the meters. So I'm going to talk about that in a little bit more detail. But fundamentally, I believe if you can't measure it, you can't manage it. It's a very old saying that we've used time and time again. And I think it comes back to that water balance question of what is this unaccounted for water? And I personally believe if we can get the water in the right buckets and we know where it's going, then we can start to manage it. And if we don't know if a leak is in a DMA or in the trunk main network, how do we know where to send resource or how to manage out the problem from occurring? So I think we have to focus on quantifying, understanding the upstream leakage to make sure that we're spending the right amount of resource in the DMAs and in them. So to measure upstream leakage, you're going to need meters, big meters on these big pipes. So you need to have a good strategy to make sure that those meters are sized correctly, are put in the best locations to be able to break the upstream network down. And also to make use of existing meters and understand those meters. Do you actually know which asset is out there? Do you know what type of meter it is, when it was installed? Have you matched the serial number to the age that you think it is and actually checked that that makes sense? So asset records of large meters. DI meters, everyone knows about. They have to be verified, that people know where they are, what they are. They might not be very good, but they know what they are. DMA meters sometimes have been fit and forgotten. Interstitial meters, that's a fancy word for ones in the middle of a network that aren't necessarily serving a real purpose. Often don't have a clue. You might know there's a meter in the ground, but no one really knows what it was or where it came from. So making sure the asset records are there is quite important as well. Once you've got all that metering in place and you've got good high quality data coming from them, then you can actually start to do upstream losses assessments, which in turn means you can define interventions, whether that's going out finding leaks, whether that's reducing uncertainty, whether that's working with customers to prevent surge in a network, whatever it might be, you can actually say this is the right intervention to do in the area, which in turn means that you can actually reduce leakage, do surveys, find leaks, fix leaks, repair leaks, move on. Okay, so the metering. So everyone says, well, actually, if you've got these big meters, they're going to have big uncertainties around them, and that uncertainty will be greater than the actual result of your balance in the first place, so what's the point? And I think it's a valid point, but there's a lot of insight out there to actually understand and make use of the uncertainty information about meters, verification records, and our understanding of meter performance to be able to manage that uncertainty and actually inform those intervention decisions off the back of it by using that understanding. So for anyone who's not familiar with metering, effectively you can't trust the number that the meter says on it. You have to make sure that you understand how accurate that number is before you use it. So meter uncertainty is influenced by lots and lots of different factors, including and not limited to age of meter, the actual technology that's being used, so whether it's electromagnetic or ultrasonic or a turbine meter. Performance issues, so has it been stressed through its life or has it just had one sort of continuous flow going through it? And other influences. Is it installed appropriately? Has it got 90-degree bends immediately upstream, downstream of it? Is there lots of sediment in the water going through it causing additional wear? All sorts of other influences. But we can take that information and meter test records to actually estimate the systematic error from a meter, otherwise known as under and over registration. And then we can use the sample of all those meters that have been tested to actually estimate a confidence band around that error estimate. So you can end up working out how to adjust your flows to kind of get the most accurate idea of the real amount of water passing through the meter and also understand how sure you are about that number. The pictures on the slide, I should just say, are of some big meters and also of a large meter sort of test rig, a flow loop that can be used to test them. So once we've got all this information, I forgot this slide is animated, we can then use the flow data from the meters, the uncertainty information about the meters, knowledge of the customers directly connected to a particular length of trunk main network, and also any contextual information, so asset information about the network, so is it steel pipes, is it cast iron pipes, is it all PE? Events data, is it in an area where there has historically been a lot of bursts, etc., to both create a flow balance that takes into account uncertainty and also to make the best intervention recommendations off the back of it. And so this is a kind of a dashboard presenting some results, and I'm going to run through a few different examples from across 3 different companies of different kind of elements of what you can find from doing these upstream balances, just to provide a bit of information. So I said at the start, it's not a DMA, so we're not only interested in the night use period, because actually, fundamentally, if the flows are lowest through some of the meters at night, that's when they're likely to be most uncertain. So we can actually get a lot of valuable information from looking at the daytime period when flows are higher. We can actually look at the diurnal profile that results from the balancers, so the average of all the midnight points, all the 15-minute pass points, etc., to inform whether or not we might have got our uncertainty estimates correct, our meter under registration estimates correct, or whether there might be customers directly connected to the trunk main that the company isn't aware of. A housing estate that actually got connected to the trunk main and they thought was connected to the neighbouring DMA. And this does happen. This is not me making up kind of insights you can find. And so when you do this is quite a simple one, but you basically get your kind of losses estimate for the area and you get an uncertainty band around it. If that uncertainty band is sitting above the 0 point comfortably, and there's no major metering issue like one of the meters doesn't work, then you've probably got some sort of losses in the area, and that might be a loss going to a customer that you don't know about, or it could be a leak. And that's the importance of the uncertainty band. If your uncertainty band is crossing 0, then actually you might just want to get a better grip on your understanding your meters to be able to work out whether or not it's worth spending any further time there. And I think the clever bit is that this is more engineering than data science. There's a lot of data number crunching that goes to pulling everything together, but actually it's engineering insight that's used to say, well, what could actually be happening and causing this diurnal profile, or for this period of time a funny thing to occur, or if we think there is a loss in this area, which pipes in particular might be the kind of first port of call for looking for a problem. Is the cathodic protection working on that major steel pipeline? Who knows? The water company probably doesn't know. Second example here then of another was TDMA as I call them, or tiles you might hear them as, or TMAs, or upstream area, or lots of different words are used. So this is just an example of a much wider uncertainty band, but you can actually see there's a rising pattern. So even if the real losses were sitting at the bottom of the uncertainty line, it's rising, and so it's a growing problem. So you might want to prioritise this area to try and find out, is that a metering issue, or is it a growing leak in the area? So as I said before, in terms of making those intervention decisions, where that uncertainty bar sits matters. In the top example, which is just some monthly estimated losses, there's 2 very large meters in this area, 300 millimetres, and actually our recommendation is to verify those to work out, to try and reduce the size of that big uncertainty bar so that you can actually work out whether the genuine result is sitting above that 0 line, because otherwise you might be chasing a leak that doesn't exist. In the second example, the bar is sitting above 0 and it's growing. And in this case, we'd actually say, well, we think there's a problem or something going on in the network that's worth going and spending some time investigating. I just wanted to highlight this example from another area. So it's just a sort of extract of an upstream area summarised, really. And we've got 2018-19 losses in the sort of left-hand number box and 2019-20 to date in the right-hand boxes. Now, this company had previously not done any balance work across their upstream network, but they obviously have DMA level leakage estimates, etc. And we happened to include doing 2 DMA tiles in this because they had quite a significant amount of upstream network that couldn't be separated. And so one of the DMA tiles, and it looks a bit messier than you'd expect from an upstream one, but there's hundreds of customers. We've got 2018's water use. Unsurprisingly, big spike. It was hot, it was dry, everyone had their paddling pools out. Came back down during the winter, and then they saw a similar pattern in 2019. They went, 2019 was not as warm and beautifully sunny. So this company had been sending out resource to this DMA to look for leakage ever since they spotted this rising pattern. No knowledge of what was going on in the upstream network. So we came along and produced an upstream balance for it. And unsurprisingly, 2019, we saw this, a massive downward scale, so it's dropping down to the negative. Now, that piece of insight led us to say, we're suspicious of this meter. We think that meter is not recording correctly. And sure enough, the water company went out, looked at the meter, and it turned out it had, it was drifting. The performance was changing. I don't know the cause of that, but they have now rectified the situation, brought down their DMA leakage, causing much cheering amongst them because it was quite a significant volume. And actually, they can accurately work out now what that DMA leakage is. But they'd spent 4 months chasing mythical leaks in a DMA, crews out sweeping, looking for leaks, because they hadn't got that kind of other side of the meter issue. And this is why I think upstream stuff is so important, because what's the point of chasing leaks in DMAs if there's actually problems either at the meters or upstream? And you wouldn't know just by looking at the DMA flow. And I think my sort of final bit before I hand over to Ant, who talks a bit more about doing practical surveys, is that you can actually combine then all of these smaller areas together. And again, you then remove uncertainty, because obviously if you get more meters that become interstitial, so you can kind of ignore the performance of that particular meter and you end up with a larger kind of area zone. You can also often see compensatory effects. So for instance, this TDMA here has a positive, but this service reservoir here has a negative. Actually, probably it's the meter or uncertainty there that's causing the issue. So they cancel each other out. So if you put them in the right order, you can see which of them cancel out and which of them actually genuinely might have a leakage problem to get you your total at the end. Oh, yes, so this is the segue really to ants. This is a final example from another water company where we'd done a tile balance and thought there was about 2 megalitres a day of leakage in an area. So the company in this case was Welsh Water, who went out. They confirmed that the meter flows were correct, the data we were using was correct, and subsequently asked our infrastructure team to actually go and survey in the area to try and find the source of this potential leakage. So inspection by our team identified the location, Welsh Water repaired it, and as you can see, this is a before, after, red and green. They did reduce by almost 2 mLD, and importantly, that uncertainty bar is now crossing 0. So the remaining bit could be just as a result of the meter accuracy. So that's my segue really to Ant and his inspection stuff. Oh yes, sorry. Yeah.
Sure we got that one. Okay, thank you, Carmen. Good morning, everybody. So yes, you've heard Carmen talking about the metering side, so identifying where potential losses may be. And I'm going to talk a bit more about the sort of practical side of things, where we've actually been out and doing surveys and what we actually find in practice. I think it's fair to say that for many years, trunk mains have not been seen as a problem for leakage. And I guess that's partly down to the fact that they are large, strong structures. Typically, if they're going to fail, they'll fail catastrophically, but thankfully that's quite rare. So people, in essence, believe that we don't see leakage from them. People do walk lines. Traditionally, that was the way really of finding leaks in trunk mains, walking along the ground, spotting the damp patches or the green grass in the summer, and identifying where leakage is. But what we found is that actually leaks can occur quite often at joints, and I'll come to that, in these large pipes. So the pipes themselves don't fail, it's the joints that are failing, and it's the joints that are leaking and resulting in quite significant losses actually from trunk mains. But because the pipes are strong, they don't fail catastrophically, so you tend not to pick them up as being a particular problem. So there's really 3 technologies I think are probably the most applicable to detecting and locating leaks in trunk mains. The correlator, which we heard about from Joe earlier, obviously developed, I think actually I would say it was in the 70s that WRC were working on it. Malc can probably back me up on this one, because I think it was, sorry, but possibly just with knowledge rather than actual genuine, with actual being there at the time. But the correlator has traditionally been used on the small networks, small diameter networks, very good on metallic and smaller pipes, and has in the past had struggled on large diameter pipes just because of the physics of the way the sound travels. Just for those who don't perhaps know how they work, but basically if you look there, you have a leak between the sensors that you've attached to the pipe. The sound travels along the pipe and you pick it up at remote locations, and by measuring the time delay in the sound arriving at the two locations, you can calculate the location of the leak between those 2 points. But it does rely on the sound travelling down the pipe, and as I mentioned, the physics means that that in larger pipes the sound is attenuated quite quickly as you move away from the leak, so it can be quite hard to hear certainly smaller leaks. And in non-metallic pipes or plastics, the sound is dissipated more quickly as well. Next technique I'm going to have a look at is Sahara, bottom left there. That's an in-pipe acoustic leak detection tool. So that's a sensor on a cable moving through the pipe and picking up the sound as it goes. And finally, we'll have a quick look at Smart Ball, which is similar acoustic detection, but it's a free swimming device, so it rolls through the pipeline over long distances, collecting data as it goes. You download the data at the end and analyze it to find the location of leaks. So I just got ahead of myself slightly there on the correlator. So this just explains it in a little bit more detail. So you can see you have your leak in the center here. That's the one I have to avoid. The sensors located on existing fittings, hydrants, valves, whatever it might be, on the pipe at either end, and the sound travels along the pipe. You carry out correlation, so that's where it gets its name from, which is just comparing the two signals in time and looking for the time delay between the two signals, and that allows you to calculate where the leak is. Improvements in correlator technology means that it's now becoming more widely used on trunk mains, more successful, finding leaks over longer distances and slightly smaller sizes. So it is a technique. The thing to be wary of, though, is obviously if you start looking at very long lengths, while you might get a result which says, I can't find any leaks, it might be because it can't hear the leaks, not because there are no leaks there. So it's just worth bearing in mind these factors when you're looking at different techniques that you might apply. The Sahara system was actually developed again by WRC. So the correlator was initial research was done at WRC, I think, as I say, in the 70s. Sahara we looked at in the early 90s, started developing it in the early 90s, and that was as a direct result of awareness of the limitations of correlation in big pipe. So we decided that, yes, if you could put a sensor in the pipe, have it travel along, you were going to go past any leaks that were there, and you're going to be able to detect them. We've coupled that with a locating device so that now if you detect the leak with the sensor, the operator at the vehicle is able to stop the cable, position the sensor at the leak, and use the locating device then to pinpoint the sensor, which if it's sitting directly over the leak, they can put a mark on the ground and identify exactly where that leak is. And this is something we've actually been using for over 20 years now, particularly with Thames Water, and I'll come on to some results that we've got from that system shortly. The operator gets a number of different displays, but primarily what we're looking at there is the sound signature. So you can see as you move along the pipe, so from left to right, that's the moving along the pipe. We see a peak in the absolute level, but also we're seeing a change in the leak noise characteristics. So we're seeing higher frequencies occurring, which is represented by the bottom edge of the graph, and the low frequencies are actually also building up. Helps us, that data helps us pinpoint precisely when the sensor is sitting at the leak. We've also developed the sensors for Sahara, and we have a sensor which can be used on plastic pipe. Although we can use the acoustic method perfectly well, we find that actually you can use an electrical conductivity method to find leaks in plastic pipes, and that'll also pick up then metallic fittings, so it can tell you whether your leak is at an air valve or at a previous repair potentially. So it's additional information that you might get from carrying out that survey. What we're seeing there is results from inspecting a 950 metre long pipeline, and you can see peaks which correspond to, they're actually metallic fittings on the pipeline. Slight difference in the two signal levels here because we've got some new PE pipe which has a slightly different characteristic signal to PVC pipe. But very clear, that graph was literally drawn out as the survey was carried out, so no post-processing on that at all. It gives you very precise information. You can actually zoom in on those peaks and measure how long the fitting is that was used to make that repair. SmartBall is a free-swimming acoustic device, so that logs acoustic data on board. It can be introduced into the network at an air valve location, for example, and extracted downstream some many kilometres away using a capture device. It rolls along the bottom, collecting data as it goes, so the data is time-stamped. So we need to know where we are at specific times during the survey. So monitors would be put on the pipe to monitor passage of the ball past particular points in the network, and that helps improve the accuracy of the results that are recorded. So there's tracking technology in there, tracing technology. It has a gyroscope to help map out the route it's taken. And as a result of that data, you download it, compare the position data and the time-stamped acoustic data, and that'll allow you to pinpoint the locations of leaks. And both Sahara and SmartBall, because they are travelling, they're travelling along the pipe and going right past the leak, they're never going to be more than one pipe diameter away from any leaks that might be there. So that makes them particularly sensitive to leaks. So we're able to find virtually, well, we believe all leaks that are occurring in pipes. I'm going to skip past that SmartBall one. It's an animation of the technique. If anybody's really keen, I can talk to them about that later. What I really wanted to get to, though, was the sort of results. So, what is the problem with trunk mains leakage? Well, with Sahara, over the last 20 years, we've surveyed, 2,875 kilometres of cast iron pipe. That includes resurveys, and our biggest customer, Thames, we actually sweep round their network once a year and are repeating surveys. But in that period, we found 3,400 leaks. If you just look at what the average distance between leaks is, that's 842 metres. And bearing in mind that we've been through the network, they've repaired, they don't repair all of them, they will leave the very small leaks which are probably not economic to repair and monitor them. But what we're seeing is leakage occurring at around every 840 metres, we're finding a leak. And the average size of those leaks, because we're able to give an indication of size, is around 0.15 MLD, or about between 5 and 6 cubic metres an hour. So I think you'd agree there appears to be a problem there. If we look at cast iron, so just the first survey at each site, clearly the figures are likely to be worse because these are probably pipes that haven't been looked at. Well, they've probably been in the ground up to 158 or 180 years, some of them. So the first time we've surveyed, the first survey total is about 546 kilometres. The average distance between leaks is around the 500 metre mark, and that has been consistent over the years. And when we look at cast iron pipes, both in the UK and wherever else we've surveyed them, and also other pipes with lead-run joints, so that might be concrete pipes that we've seen overseas, some steel pipes as well, we find a very similar figure of around one leak every 500 metres. Steel pipes, we've surveyed less, fewer leaks, but again, look at that figure. It's not that different. Interesting, I believe, the number of leaks that there are out there, and as I say, the average size is around 5 cubic metres an hour, and that's we've worked with water companies to look at. We assess a size band when we detect the leak, and then ask the water company to verify that when they repair it. At concrete, I mean, clearly concrete is far fewer concrete pipes in the UK. Those figures are mostly from Morocco and Portugal, in fact. Slightly better performance there, slightly newer pipes. Okay, thank you very much. I'm sure Carmen and I will both take questions now.
Mostly a question for Carmen. Thanks for your presentation. Agree with a lot of what you said. One question I had really was, as you mentioned early on, a lot of the water companies aren't seeing trunk mains as a big problem. And when you do this kind of analysis, it highlights that there is more leakage out there than we currently think. How can we go about convincing the water companies of this and to do the kinds of analysis that you're talking about?
So I think it is changing. We first started trying to do this with some companies about 6 years ago, and they were kind of a bit different. As I say, we're currently working with 3 companies and talking to more. I think the consistent measures report has helped, and also a 15% target of reduction helps, because people want to really spend their money most wisely, and actually it might be cheaper to find some leaks on the upstream network. I think it is important to say it doesn't necessarily increase the total leakage by actually understanding how much is occurring in the upstream, because you might be reducing it off the DMAs. So it's just a case of actually understanding where the problems exist. And similarly to, I think later this afternoon, we're talking about, is it a supply pipe, is it a internal wastage in a customer's property? If we actually understand, is it PCC, is it a leak, we can do something about it. We can put in place the right policies and processes to fix it. So I think the tide is turning, and often just giving it a go in a small area shows how valuable it can be.
I'm interested to know where the original belief came from within these water companies that trunk mains are not a problem, because I have heard it a lot of times, both in the UK and overseas.
Yeah, I'm too young to answer that. Here you go.
I think it is just genuinely that there's not the anecdotal evidence probably that they're a problem. That, as I mentioned, they tend not to fail, and leakage very often we find leaks, and the water is just disappearing into the backfill and running away. We've found leaks of the order of 5 megalitres a day. That's frankly a burst almost. And there has been no evidence above ground of that occurring. And that's not just an isolated case. We have found several of that size, where, in fact, in one case, the water was coming out of the pipe and going into a sewer, an adjacent sewer. But in other areas where it just runs into the ground and is lost. And I think it's the fact that it just doesn't appear at the surface necessarily that causes a problem. And it may be that they're distributed so widely that actually they're not, as a percentage, it's not a huge volume. That's a percentage of the total volume passing down the main. At an absolute level, it's important, but as a percentage of the total volume, can be relatively small.
So obviously again, Trent. Do any of the methods tell you anything about the likelihood of the leak turning into an eruptive burst?
Sadly not. I mean, we are detecting the condition of the size of the leak as it stands. So yeah, we're pleased to say that we're able to at least give you an indication of the size, so that should be helpful. And then if you can indicate whether it's at a joint or whether it's in the barrel of the pipe. I mean, clearly if it's in the barrel of the pipe, act now. If it's at a joint and it's small, certainly in a lead run joint, then typically we would advise, monitor it perhaps, particularly depending on where it is. If it's in the middle of a field, okay, perhaps you want to go and mend it. But if it's in a very difficult area, you might just want to monitor it. Oh, sorry.
University of Birmingham. I just have a question about the last slide that you showed us about the pipes. So, does that give any indication about the types of the pipe or the leakage, or it's about the age of the pipes? So, is concrete is the best option that you would like to prevent the leakage? Or?
No, I'm not sure that that's necessary. I mean, what you'll notice, obviously, there's no ductile iron showing. I think it is actually maybe on maybe was on the bottom, but clearly ductile iron would show up as well. It actually shows up quite poorly because the ductile iron inspections we've done have been specifically to go and find a leak that's known about on a pressure test of a new pipeline very often, rather than just a random leakage detection. So ductile iron would look good, but might look poor, but actually its performance generally would be better. The cast iron is virtually a random sample, but it is heavily biased towards work in London. Freely admit that. But where we have got data from other areas around the world, it's been shown to be sort of similar. And the concrete, that actually includes a lot of resurveys where there have been repairs done in the meantime. So it is a slightly skewed number. I think it is quite skewed, actually. I think if I'd gone through and done the first surveys for the concrete, it would look worse than it does. So I wouldn't read too much into the sort of lower numbers. I think what I'm saying is we've got a lot of cast iron in the network. I'd be out there looking at it.
Thank you very much. And of course, if you have more questions for Anthony and Carmen, I'm sure that they'll be more than happy to answer them during the lunch or refreshment breaks. Our next speaker is going to be discussing trenchless solutions, slip lining with GRP pipes. Jarle Hausberg, I hope I pronounced that correctly. He's a qualified civil and construction engineer. Began his professional career as the head of water and sewer department in a Norwegian municipality back in 1983. And for the last 16 years, he's been the managing director of Amiblu Norway. Thank you very much. You have to clip this onto your suit.
Yeah, thank you and good morning, everyone. I'm coming from Amiblu, and Amiblu is a joint venture between the technology Hobas, which is EC pipe, and flow-tight filament bond. But not going too much into that detail. We have 6 plants in Europe, 3 for each technology. So a high capacity. We are generally supplying pipe for all kind of installations. We are today going to discuss different kinds of slip lining for pressure lines, sewer line, stormwater lines, etc. But our main market are also in water, sewage, industry, hydropower. We're also doing a lot of jacking, and all within the European standards for GRP pipes, following also by all the American and ISO standards. These days, environment is in focus, and with all respect, GRP is among the best products. A lot of analysis has been done and showing that we have a very good material in that respect. Also has to be taken into the consideration. One of the big advantages, of course, is also that we have a non-corrosive material with a very long service life. And just to show you, before we go more into the renovation, relining, this is the product range from 200 millimeter up to 4 meter in diameter. Pressure pipes up to 32 bar. Standard length 6 and 12 meter. particularly for slip lining, it can be also from 1 meter and whatever length is suitable for the job to be done. And of course, a full range of fittings can be tailor-made, like also manholes, etc., what you need on the pipeline. What we are talking about is a typical composite. It's not a homogeneous material. It's a composite of polyester, glass fiber as the reinforcement, and some filler. And depending on the flow tight or Haubas production process, we have quite similar way of building up the pipe with the structural skin on both sides and the core in the middle. The standard products will be with standardized pressure classes and stiffness classes. In special occasions, if there is very high abrasion, if there are special chemical requirements, we can also do special liners to have a pipe which can stay for longer than a standard pipe. But normally in municipal work, a standard pipe is very suitable. Slip lining with GRP pipes. There is a lot of control and evaluation that you need to do before you go ahead with slip lining in general, or with renovation, of course. And the corrosion on the existing pipe, damages, if there are some breakdowns inside the pipeline, if there are curves that you even don't know about before you're inspecting the pipeline inside, the diameter and which diameter can be possible with a new pipe, possible pipe length, both from entrance possibilities and the curves in the line, structural strength needed. Sometimes you have corrosion on the old pipe, but the pipe is still strong enough for years when you do the repair work. But in some cases, you also need a full structural solution with the slip lining pipe. And of course, you have to evaluate the health and safety, especially when you're having people working inside the pipeline on the big diameters. That's a critical point in many cases. Some of the advantages, it's a corrosion-free material, which will stay then for a long time. We are today quite sure that if our pipes are installed the correct way, it will stay for at least 150 years. And when we see all the problem on traditional materials and so on, we see more and more waterworks, utilities, etc., which are requiring 100, but also starting to discuss 150 years. It's a low-weight material, so it's suitable for the transport into existing pipelines, depending on how you do it. And optional length, as I said, we can produce whatever length is wanted and optional. Limited wall thickness, so that we are not reducing the capacity of the existing pipeline too much, but still having high strength. And we have various joint possibilities. You can have traditional couplings. We can have a lock joint biaxial solution with axial strength. And we can do lamination work so that you get the same material in the joint, so to say, as in the pipe. Several ways of installation. And to transport the pipe inside the pipe or the borehole, joining together outside or inside. It's pretty much also depending on the diameter that we are working on. On the bigger one, in many cases, the jointing is inside the existing pipeline. For the smaller diameters, normally we do the jointing outside and pushing or pulling the pipe into the existing one. You see some pictures Here we have a borehole in the mountain that was slipline. Get back to the project, but there are steel bars as a track to push it in. We have special trolleys that has been used to transport the pipe, the bigger sizes, with spacers, just pushing them in. And in some cases, even with a crane beam in the top of the old pipe or in the borehole. Of course, there is a lot of influence on a pipeline in the ground, and this has to be evaluated also when you do slip lining, especially when the old pipe is in the condition that you can expect a collapse. You partly have a collapse already in many cases. And then of course the traffic, the total load, and also the groundwater level is of course of big impact. Inside, like in sewer pipes, you have the sulfuric acid, and that's one of the big advantages with GRP, which is non-corrosive material in that respect. When we do the slip lining, one of the advantages with GRP and this kind of work is also when you have the bypass pumping. In some cases, it's difficult to get it completely dry, and with other methods, some of them, that might be a requirement. With slip lining, it's not that big an issue, and we have even had jobs that has been ongoing, and we have got heavy rain, and on combined storm sewer, we got a flooding into the pipeline. Generally, it's more or less just to flush and clean and continue the work, which would be impossible with lake cured in place and some other alternatives. When we have the existing pipe, borehole, whatever, and we have a new pipe inside, there is, for the grouting in between the two pipes, of course it can be more in the center, depending on how it's installed. But sometimes you have the possibility of drilling into the pipe from outside, filling up the gap in between. In some cases, we are pulling together with the pipe through the old one. Also injection pipes. In one project, I will show cases later on, 80 millimeter polyethylene, and with different distances, and we were just filling them up when we were doing the grouting. In other cases, we are supplying the pipe with nozzles so that you can also do the grouting from the inside. Generally, for grouting in slip lining, we have been involved with mostly concrete. It can be lightweight concrete, concrete with very good flow properties, so that you can fill it up from more or less from one end to the other. And of course, what's important is the control of the casting pressure when you start to fill up in steps. Alternatively, you can also fill up the new pipe with water. If you have a steep slope, then you're also compensating the inside-outside pressure difference. Alternatively, there has been used backfill also with sand and gravel and lightweight aggregate like leca, etc., that are blown into the gap between the two pipes. The problem is to get a full 100% filled gap, and if you have settlement then or a crack on the old pipeline, you can get punctual loads on the new pipe, and you can also get settlement in the ground. But of course, the advantage with gravel and sand and LWA is the possibility of taking the pipe out again, which is much more difficult when you have grouted it in concrete. Yeah, in addition to round pipes, we also have a big production of non-circular, and that's also used in many cases for slip lining, just to show you a few samples. A few cases. In Stavanger on the west coast of Norway, this is the portable water line. It's a borehole in rock, which will be similar as an old pipe in many cases. And it's a 1200 millimeter PN10 potable water. And there was two borehole. One was 175 meter and one was 230 meter. And they drilled a hole of 1404 millimeter. Then they built a track through the borehole with 50-50 x 3 millimeter steel bar. And the pipe was jointed outside on the track and pushed in by an excavator. We see there was a buffer, just a cylinder, taking care of if something happened, and they monitored the pressure on this cylinder. If there was something increasing the friction or stopping the process, they had 1 meter also to collapse the cylinder because there was a safety valve before the excavator was putting on too much force to the system. We were testing, pushing two pipes against each other inside the coupling, and before this job, and with a 1 degree angular deviation inside the coupling. And the measurement we did stopped because of technical issues with the equipment, but we had 85 ton without any damage to the spigot of the pipes. And in this case, the maximum, even on the 530 meter long borehole, the force in equivalent to tonnage was like 25 ton. When you had a pipe sliding on the steel bars, you had a friction factor of approximately 0.3, and we could push the total length of 530 meter when we pushed the last pipe into the tunnel. And this installation was grouted by a very lightweight floating concrete. So they were filling up from one end, and it was floating through the whole pipeline or the whole borehole. The weight of the concrete, the density was less than 1,000 kilo per cubic. So by filling up the pipeline was lying on the bottom in the borehole through the full installation. And this was installed back in around year 2000, so it has almost been in operation now for 20 years without any problems. Yeah, kind of similar project, slightly higher pressure, also potable water on 800 millimeter in 1100. In this case, it was done slightly different with the grouting, because here we had 80 millimeter polyethylene pipes following the pipe when we were pushing it through. And then we had steps. The first pipe went into the bottom, and the next one like 70 meter further up, and then 70 meter further up, and we started with the one in the bottom. Also here we had a pipe water filled because it was quite steep installation, so to compensate the difference in pressure, the pipeline was water filled, and also to keep it in place during the installation. Yeah, this is more just a road crossing and just to show also with spacers. Then it's more in the center of the existing pipeline. This was a steel pipe that was jacked under the highway. And in this case, it was secured by blowing in lightweight aggregates like leca. Because on pressure lines, you have to make sure that you also have a stabilization of the pipe. Depending on the diameter, of course, you see in the garden hose is starting to move around just to instability very quickly when you have a pressure on it. And with high pressure on big lines, you also have to take care of the stability, but also to secure that the pipe is not going out of the joints. Another, this is a stormwater and sewer project in Sweden, existing 2000 millimeter. And after they had controlled it, they found that 1800 could do the job. And even if it's a difference of 200 millimeter, with a smooth bore of a GRP pipe, you are not reducing the capacity more or less at all versus an old concrete pipeline in this case. The installation was under a highway and a parking area. And in total it was like 444 meter. And the access point was in an elbow in the middle. So they did the slip lining in two directions. And then as the last piece to be put in place, they put in the elbow before the grouting. And here you also see they had a special, quite a simple trolley in both ends of the pipe and manually pushing the pipe through and connecting them inside the pipeline. And the grouting was done by and through the nozzles we supplied on the pipe, with the concrete then from pumping in from the inside of the pipeline. A little bit special slip lining. It's an old hydropower station in Denmark. There are not that many of them in Denmark because Denmark is more or less 100% flat. The highest hill in Denmark is 177 meters. But they have, like this one power station, and this has been in operation since 1920. And they wanted to keep the visual environment of the old brick station, and they upgraded the machinery. And the pipeline was old steel pipes, and it was sandblasted and painted. And then they were cutting off just a piece in the top and slip lining with 1600 GRP pipe from us, filling the gap with special concrete. And afterwards, it looks like, and this is today a living museum. It looks like the old pipe is in operation, but inside there is a GRP pipe. Yep, as I said, non-circular, a big job in Krakow. Very special. You have also banquettes and a dry trough, and then you have the flooding for the stormwater. So huge capacity and self-cleaning when it's only sewer in a dry period of time. And as you can see, a lot of different diameters, and the total job was a pipe supply of €2 million. Then a little bit a special project. I have a few slides on this one. It's in Oslo, and the most central area of Oslo, Majorstua. And there was a big problem with the sewer tunnel, which are constructed from 35 to 49 meter under the surface, the street level in this area. And the problem is that there was so much leakage into the tunnel that the groundwater level was going down, and Oslo Waterwork had to, via wells, pumping in water, maintaining the groundwater level for many years, because it came under the fundament of the old buildings. And then you get settlements, because it was very often oak timber as fundaments, and when the groundwater go down, it rotten, and you get the settlement. So that was the requirement also to build up a groundwater pressure against the tunnel again with minimum 10 meter head, and 70% of that already are in the first year. There should be a lifetime documentation for service life of 100 years of the solution, and it should take 50 meter outside water pressure with a safety factor of 2. And optimized DN, the minimum requirement was 2.2 meter. The old tunnel was of different diameters, but in some areas they had been doing some old concrete works, and it was down to 2.4, 2.5 meter. So we ended up together with Skanska to sit down and do a lot of preparation during the tender phase, and prepare everything, the logistic and how to do it. It was one access point, and it should be in the length of 1150 meter into the old tunnel. And after having a tolk, as we say in Norwegian, a dummy to go through and see which length of pipe was possible in the curves and which diameter could pass, they ended up with a 2.3 meter and length of 4 and 2 meters. The reason for the two lengths are in some of the curves we took the advantage of the angular deflection in the coupling and made the curves without having to produce any bends inside the old tunnel. Of course, when you're pumping concrete, and you know, it's easy to have a separation of the concrete. So Skanska and the supplier of concrete did a lot of actual testing. So they had here in an area a full test of dropping the concrete 50 meter down under the surface and pumping it like 300 meter before it should be grouting between the new pipe and the tunnel. So they found a good recipe for the concrete that works fine, and then they could pump it, and it should also flow 24 meter in the grouting area, because the sections for each grouting was 24 meter of installation. Here we see a number of pictures. A very special trolley with its own engine and hydraulics. So it was driving into the pipe, lifting the pipe, and driving into the tunnel. When you are going to put 4 meter and 2 meter pipes at the time, and you are starting almost 1200 meter in, the logistic is of course very critical for the installation and the schedule. And then you see in some areas, because it was also a very strong requirement that there should not be any water going in between the rock and the pipe. So there was injection both between the pipe and the concrete and the rock with epoxy after the grouting was done. Here you see the section was blocked with the foam. Yeah, I see we are soon. The result was very positive. The client, the Oslo Waterworks, was extremely happy with the installation. And already the same year, we had results for the pour head above the tunnel, which was more than the requirement for the 5 years. And this was also, as one of the other projects, the Scandinavian Society of Trenchless reward for the best project of the year. So that's it. We also like to thank some of our UK clients for a project that we have been through. So thank you for your attention.
project so far in terms of the length that you've had to do?
On slip lining, of course, you mean. The longest section in one section and with one access point, I think, is the big one in Oslo, the 1150 meter.
Very impressive, I'm sure everybody agrees. Okay, thank you very much.
Thank you.
Thank you very much for that. And again, if you do have questions for Jarle, then I'm sure he'll be really happy to answer them during the breaks. We're now going to ask Robin Bell from Infomatics to join us. And Robin's had senior roles in a number of large technology-led companies, but now he is the Chief Operating Officer for Infomatics. Can I just ask you to click that on?
Sure. Okay. I think I'm going to I'll ditch the microphone. Can you hear me okay? I'll try and shout loud. It's okay. Oh, you. Okay, you can't hear, right. Hello, can you hear me okay? Does that work? Right. I've got too many things I've got to press here, so we'll see how I get on. I'm the COO at Infomatics. I cover commercial activity, also the development activity, as well as the logistics of manufacturing our product, which I'll talk about in a little bit more detail. So I'd like to talk about why we do what we do, and then talk about how and then what. It's really important that as a supplier we think about the problem we're trying to solve, so it's kind of all about the why. But first, who are we? So you can see there a bunch of smiley faces, including mine on the right, but Dr. Mike Williams is our CEO. And we also have Dr. Ivan Stoyanov, who I think a number of you in the room probably are aware of Ivan, who have come across him before. He's at Imperial College, and he's really the founder of our business. Peter Collins is our chairman, and we're also backed by investors, but most recently the Suez Group, who made a minority investment in the business, and we work with them engineering-wise, but also commercially, and as I say, they've invested, which is a terrific step forward for us. But what's most important to us is we have pretty much a technical team. Even though I have commercial activities, I've been a design engineer for most of my life, and we're basically striving to make a difference. That's why we're there. So we came out of InfraSense Labs, which is essentially Ivan Stoyanov's sort of commercial, semi-commercial part of Imperial College. And we've been around for about 4 years, since September 2015. Most of us have been there for that period, and we've grown during that period. What sits behind our technology is some quite unique intellectual properties. So that's what we're looking to exploit commercially and to the benefit of our customers. We've shipped around 1,500 systems, but actually that number gets out of date sort of daily. The last quarter of this year is going to be very busy for us, and we're hoping for a busy next year as we go into AMP7. A number of key clients. We continue the R&D, and I'll talk a little bit more about that later. So why are we doing this? At the very highest level, about 2/3 of the world's population has a water scarcity for at least a month a year. There are so many different ways of expressing this, but as a global company, we need to address not just the UK market, but beyond. And it's quite clear, a few key words: improved operational efficiency. We know about the regulatory influence, particularly in the UK, but also we see that around the world. The regulators are starting to wake up in other parts of the world. And all this pressure needs sophisticated network monitoring, analytics and control, and somehow that needs to be integrated, because nobody wants yet another dashboard to look at more data. So we have to think about integration. And yeah, another one of these charts, and it's kind of the other way around to yours, Joe. But what I love on this one is Bulgaria. Actually, that doesn't work, but Bulgaria's on the left. So I've been to Bulgaria a couple of times. That even they talk about, and their regulator talk about 60% water loss, but we know on the eastern side near the mountains, they have up to 85% water loss. However, as a market, we found it not very easy because they have no money either. So maybe at some point they'll figure this out, but it's really quite a challenge. And you can see us there. Okay, we're towards the right-hand side, but that clearly still isn't good enough. So why are we doing this? What's different about our offering? So what's important to us is that there's attention to detail of what's going on in the network. There's a lot of pressure logging of systems every 15 minutes, reporting that data every 15 minutes. There is a huge loss of detail in doing just that. So in this particular case, excuse me, 80 meters of pressure variations are just completely missed in that case. And these few slides just show it in a bit more detail. So the blue there shows 15-minute data. If you start to measure at 1 sample per second data, so this is in the pressure domain, we're looking at time versus pressure in meters of water, you're starting to get a bit more detail. But actually, you need to go down to some very high frequencies in terms of pressure measurement to see all of that detail. Now, some people, regularly people ask why 128 samples per second. And it is actually about oversampling. So Nyquist is the theory of oversampling communications. It applies directly to also pressure measurement. And we're oversampling to get clean edges on high frequency data. We've calculated, we've worked the 128 is enough. Some people do go higher. We don't think it makes much difference. I think if you go lower, you're starting to lose stuff. So we have a particular metric we call cumulative pressure-induced stress. This came out of Imperial College. It's a very good metric in calculating not just the single effect of transients. I try not to talk about transients because a transient is a single event. This is about dynamic pressure variations in the network. So what we do in simple terms on the left-hand side there, we're collecting the data. We're then using some software tools to summarize that data, to make it achievable in low-cost hardware and count the variations, even if they're tiny compared to larger variations, and provide a metric. And you'll see how we can use that metric as we go forward. This is an interesting one in terms of a particular pipe break where, sorry, Bob, I think it might have been on the Severn Trent network, and you might even recognize it. So that's a longitudinal crack down the pipe. Transverse cracks as well are affected by these transients. But this was analysed at Imperial College, and the fatigue-related stresses were pretty clear. So we know that this metric is really, really important. We also did a great bit of work, again with Severn Trent and also with Imperial College. This is going back 6-7 years, kicked off within the innovation team at Severn Trent. And what we essentially were able to prove is kind of intuitive, but there is a link to a higher cumulative pressure-induced stress. So adding up all those variations with a burst rate per 100 kilometers, if you can't quite see that slide. So there is a positive correlation. It's really important to understand that correlation, and it's vitally important to do something about it. And I think the industry is starting to realize that preventing, we've heard prevent mentioned a couple of times, is really important. So understanding this and then applying it is where we need to go. So can you put your hand up if you've ever heard a transient? More than I thought, but that's tremendous. So you're going to hear one again. And for those who haven't, hopefully this will be somewhat revealing. Now, we're hoping the sound is set right. This could affect your eardrums. So this is an industrial location. I can't tell you where it is, but there are pump banks here. You'll see the pump switch from one bank to the other, and you'll see what happens. So I'll probably end up playing it a couple of times. So here we go. So I'll just reverse that and show it again. So you can see the pump go and the significant movement of that pipe. And that's literally due to pump variations, and that's actually what it did to the pipe. So if anybody was in any doubt about what high frequency pressure variations, transient kind of effects can do, in this case it's effectively a pump surge effect, then that's a good indication. So I have a second one. Now this was done at in a university installation. It's a transient rig that was created, and what's interesting here is the time it takes for a transient to be created and to dissipate, and the cavitation effects you actually see in the water. So again, I'll kick that off. Sounds working well. So you can see the cavitation effects there, and that is literally air and water moving through the network, and just wait for those delayed reactions. There might even be one more. No, that was it. So they are huge, these effects. They need to be mitigated. And again, they're really very physical. So I'll continue with the slides. So how do we address this? What are we doing to deal with these effects? So the first thing we're doing is we're trying to provide actionable intelligence, so information to hydraulically calm networks and reduce pipe stress. We sometimes call this our network narrative. The second thing we're doing is looking at automatic network control to optimize pressure management and to improve efficiency and reduce operating costs. This whole approach is applicable to distribution and transmission networks. So I'm kind of pleased I'm in this section because it feeds into, I think we'll be talking more about distribution in a minute. What we do is not only these devices, so we use this device to measure high frequency pressure variations. We actually didn't want to have to create a device to do this, but we couldn't actually find anything with the right accuracy in the time and pressure domain, and we needed to make sure we could get that information into the cloud and to be able to use it. So, but we're not only the device, we're also analytics. This is our network narrative approach, but also we're working on control methodologies, and in this particular case working with a company called Clayval, who do pressure reducing valves, which are the primary approach for us to introduce calming methods. So I sometimes talk about inflow sys, and inflow sys is the entirety of our solution in this product space. So we have a platform. It's a cloud-based platform, as you might expect. It's called InflowNet. We have the InflowSense devices, the great big, rather small, green thing we have there. That is fed by what we call InflowSolve. It's an analytical platform where the hydraulic modeling solutions are put together. We, I guess, pride ourselves on working on data, but from a hydraulic perspective. We don't believe you can just look at data, that you need to have that hydraulic understanding. And that's come up in a few of the presentations we've heard already. We have an InflowNet web application, so you can actually look at the data. But actually, more importantly, our customers, the utilities in the UK, worldwide, they really need that integration piece. So we'd rather not do the web platform. We recognize we have to. But we need to feed alerts or alarms, whatever the terminology the company uses, into the operating system that's used by the relevant utility. So that also is important. Now, I'll give an example. We don't have enough time today to cover a whole bunch of things, so apologies if I skip over things quite quickly. But we, as one of our product offerings, we're looking at localizing events, transient type events in the network, and in some measure we can do that for bursts and leaks where there are changes in the network. So we have two approaches. One is event source localization, so we can get to a certain accuracy. And the second is looking at demand anomalies using the pressure measurement devices that are installed in a DMA. For example, we usually install something like 5 devices per DMA. Some of us have been at some of the presentations where Anglian Water, who are using our devices, are doing just that. And that, as a result of analysis, on average, gives enough information to actually do something useful with. So what is an event? This is an example. It's where a transient event is where the water pressure moves from one steady state to another state. So we can detect those large state transients with this cumulative pressure-induced stress metric, but also we can detect those as individual events. And then we can use those in our analytical approaches. And then the other part of the vocabulary is what is an EN model. So it's an equivalent network model. You can see there we have a number of devices deployed. If we know the elevation, we can work out the pressure head. If we know the flow into the network, we can then do some very interesting things to calibrate the model and identify where there is some anomalous behavior. And we have a patent for a lot of our work, but this particular one is patent pending at this point. And really just showing an indication of how the information for localization can be presented. This is our latest feature where initially we're doing a color map. So this shows whereabouts within a number of assets we found a correlation. It relies on really accurate timing. So the transients or the pressure measurements we make in this product are accurate to within 10 milliseconds. That's taken a lot of effort to achieve that, and we also have IP around that too. Now, to some customers, that's not compelling enough. It's good, but what we're now doing is we're overlaying that within the GIS network, and that allows us to, I wouldn't say pinpoint, I would say localize, but get closer to the source of that event. It could be a burst, but not every burst creates a signature that you can pick up in the pressure domain as a transient effect. But it allows us to find points of interest, if you like. One thing I should say is we don't see this as a replacement for noise correlation. We see this as augmenting noise correlation. We're doing some great work with Anglian Water at the moment where they have a significant number of points of interest from noise correlation, but actually sometimes you need a bit of a steer as to where to focus efforts. So again, we're working with them to bring the different technologies together. We have 2 algorithms here that work in harmony. If you add in noise, you've actually got more information, and you're using the key elements that we can measure: flow, pressure, and noise. Those are the 3 things that can give real insights into the network. So I'll finish with a few case studies, and then by all means ask some questions. Now, this was one of the first case studies we did with Suez, and it started the relationship back in 2017. I was pleased to spend a lot of time on this, actually, and this was to the west of Paris. I helped do 54 deployments in that area. And what we did, we were able to measure and extrapolate the cumulative pressure-induced stress across the network. We did an assessment in conjunction with Suez on the criticality of the various pipes within that network. And we were able to then identify where there were pipes which were the most vulnerable and where to target investment. Now, the ideal scenario for this is you overlay on top of that as well pipe condition. If we understand pipe condition across the network, if we understand from the videos what we're hitting the network with, then we stand a chance of figuring out where the most vulnerable places are. So this was a great study. We're now working with Suez on their Calm Network initiative. For those of you who've kept an eye on LinkedIn, they're looking to achieve 30 million savings across their 300,000 kilometers of network in France by 2023. So we're a part of that. and we're part of the Aqua Advanced, or doing the integration with our Aqua Advanced solution. So flipping this from detecting things that have happened to preventing things. So we've introduced our pressure management solution, and this is a case study working with Wessex Water, where you can see on the left-hand side of that plot, again, we're plotting meters of pressure, meters of water against time, and a new curve was implemented based on, there were 3 of these devices within a DMA providing information to our algorithms to create a curve. I worked at I2O Water. I was part of what we did there on pressure management, but we knew the limitations when we created informatics of just having one critical point measurement. The danger is you push the variations to other points in the network. So having multiple inputs and creating an algorithm that can truly calm the network is really important. So you can see this calmer operation from that point. And I think what's interesting here is we have a hypothesis that, yes, reducing average pressure has helped reduce the level of bursts, but actually maybe flip that around. Maybe the problems were caused, we know they were caused by the peakiness, the dynamic variations. If you can reduce those dynamic variations, maybe you can push the average pressure back up again. So it gives a bit more of a degree of freedom, because there comes a point where you can't just keep pushing down and down and down. So calming the network is clearly the focus here. And there's a little diagram there. We haven't got time today to go through this, but effectively we're working in the cloud with Clayval's data, our data, and the ability to push curves to the Clayval solution. So this is one example of what we're doing, and there are other aspects of calming that we're pushing ahead with, which are really important. So coming back to Severn Trent again, we've had a long relationship with Severn Trent. We work collaboratively to estimate potentially 15 to 20% reduction in burst rate as a consequence of calming the network. Again, Bob, you may have seen the brown paper that was circulated at one point, and I got permission to share these results, where there's some big numbers, millions of pounds in avoided repair costs, ODI benefits, and so on and so forth. It'll be interesting to overlay this on the final determinations to see how that can improve the savings. But again, same curve showing those correlations. There's no doubt calming the network does make a big difference. And this is a great example of where we worked very closely with the teams to implement improvements in the operation of variable speed drives. I think we've all heard the fallacy that you just put a VSD in, solves all your problems. It really doesn't. It needs to be set up correctly. So this had a VSD, I believe, in this particular case, 70 meters variation, and then with a lot of detail work, it's not trivial to do this, it was reduced to 10 meters. And very interesting study we did in one particular area where we monitored through many kilometers of the network to see the effect of these dynamic pressure variations traveling through the network. Just like the demonstration, they literally went many kilometers back and forth, and we could detect the dissipation as it went through the network. But also what was interesting, we looked at PRVs in a gravity-fed network very close by, and it was quite clear that the maintenance of assets under these 70 meters condition was significantly increased over the calmer gravity-fed system. So it's quite clear again that it's not just causing bursts, it is damaging assets. So coming back to the health asset improvements that Ian talked about, it has a part in that too. So what else are we doing? Very briefly, the last couple of slides. So we have an engagement with Black & Veatch, and we've come up with a DMA health index. We're looking to understand or help companies, this is a UK initiative, but help the UK industry understand the health of the DMAs. And it's looking from a slightly different perspective in terms of the calmness and how the DMA is operating. We have 12 measures. There's some, if you work from the bottom, supporting measures in terms of network models, the accuracy of those models, working to leading measures, cumulative pressure-induced stress comes back in, as you might imagine, understanding pressure target exceedance, and so on and so forth. And then moving up into the lagging measures such as lost seconds, leakage, number of bursts. The interesting thing for us is that what we can measure with this device and contribute into this health index covers 9 of those features. So working closely with Black & Veatch, we're now engaging with various utilities to see how this can benefit and how this can be integrated with other systems. Thank you. That was a rapid run through.
We can still take a few questions.
Okay.
Does anyone have a question for Robin? Yes, Joe?
You've mentioned France and you've mentioned the UK. Is this approach being adopted in many countries, or is it quite
Yes.
new?
There's a slide I often show which shows all the different territories. So we're in South America, North Africa. There's a bunch of devices. Spain, North America as well, and Australia. So there's quite a lot of adoption. Some of that has come through our Suez contacts and connections. Some of that is independently in those countries. So I'd say that probably 30-40% of what we have out there is offshore. Okay. Any other questions? We have lunch, so you can ask me others over lunch. Thank you. Okay.
Thank you very much. Oh. Thank you very much, Robin. And like I said, you can ask him some questions once he's hopefully finished his lunch. So now we could break until 1:30. I think maybe 45 minutes should be enough for lunch. Well, maybe if you eat as quickly as I do, maybe we could come back sooner. But I think we break now and then reconvene. We've got a fantastic programme this afternoon for you. Thank you very much.